Looking over the homework, I realized that we kind of went over the law of conservation of mass and effectively energy a little bit fast, so I wanted to readdress this. We pretty much put the law of conservation of energy and mass in just words and just said, oh, well, this is the law and that's the end of it. Well, a lot of the things that you're going to end up finding with chemistry is that it does transition between a lot of different areas. There's English, and then there's mathematics. And chemistry is trying to bridge the gap between those. So we want to be able to talk about chemistry using mathematics and English appropriately. So since we've only looked at the law of conservation of mass and energy in English, can we potentially convert it into something mathematic? Okay, so let's go through a general reaction. Okay, and I know this is a little bit new, but we can specify this. If we start with what's known as our reactants, okay, or our starting material, we want to come up with some way to show that this transition into products, okay, or an end result. Being the creative artists that we are as chemists, we say, okay, we start with reactants, we end with products. What's happening in between is the reaction. And we represent that by an arrow. Real straightforward. Okay? So when we're looking at the law of conservation of mass and energy, okay, we're looking at an initial state and a final state, and we're comparing those two states. Okay? So our final state being our products, our initial state being our reactants. So if we're going to say conservation of mass and energy, we could say the mass initially is somehow related to the mass finally. How is it related? Conservation of mass says I cannot create or destroy matter. What's the relationship between the mass initial and the mass final? They are the same, mathematically shown with equal sign. Okay, what if initially my mass is spread across 6 or 7 different things? What would my mass initial be? Well, it would be the mass, which I'll abbreviate just as M, the mass of item number 1, plus the mass of item number 2, plus the mass of item number 3, and so on. If all of those came together to make our mass final, then we know that has to be equal to our final mass. Okay? So the mastering homework does ask some questions. If you start with I think what they're using is nitrogen and hydrogen, and they go through a reaction to make ammonia, okay, or a final product. Conservation of mass says it has to be the same. The total mass on the initial side must be the total mass on the product side. Okay, bless you. Man, what is wrong with this room right now? And not you, I'm referring to allergens in the room. Nitrogen plus hydrogen goes to ammonia. If I start with, and anybody that does all the math on this might get mad at me, but 3 grams of nitrogen and say 6 grams of hydrogen. And I react those entirely. All of the hydrogen and all of the nitrogen becomes ammonia. What mass of that NH3 or that ammonia would I expect to get out of the end of this? 9 grams. Okay? So what we're doing is taking that English language and turning it into a mathematical equation that we can then go through and process, which is 3 grams plus 6 grams gives us our initial mass. And since we know the law of conservation of mass, we know that that has to equal our final mass, which equals our 9 grams. Okay? This does assume that everything reacts entirely, okay, which is an extra little wrinkle that we'll throw into this in just a second with another thing that hopefully we can see. Yes?
I'm just confused on the first one. Why is it NH4?
So ignore the symbols for the moment. Okay? What we're going to run with is just nitrogen and hydrogen make NH3. Okay? And what you're addressing is a little bit further down the road when we actually look at the equation and say, we have to have this balanced. Okay? I can't create or destroy matter, so if I start with N2, that means there are how many nitrogens on the left-hand side? On the left-hand side, if it says N2, how many nitrogens are there?
2.
2. If I look at the right-hand side, how many nitrogens show up? 1. I just destroyed nitrogen. Okay, so the equation in this case is not balanced. What we're looking at is just the overall mass results. So we're stepping away from balancing the equation. We're just saying this overall reaction occurs to some extent. Okay? So let's clear that away. Let's look at building a bicycle, my favorite example. So to build a bicycle, what do we need? And I'm going to regret asking this question, but let's see what happens. Wheels, good. I like that. It's a good start. How many wheels do we need? 2 wheels. What else do we need? Yeah, I knew that was going to happen. And we'll call it wheels and rest of bicycle. I don't want to see too many pieces, and we need 1 of those. Okay. If we go through and add this up, the mass of the wheels plus the rest of the bicycle will have to equal the total mass of our bicycle. Okay. What if I start with 4 wheels and just 1 rest of bicycle? How many bicycles can I make? Still only 1. Okay. What happened to the other 2 wheels? Exactly right. I put them off to the side. So if I was going to look at this reaction, I wouldn't say just 1 bicycle. I'd say 1 bicycle plus 2 wheels. Okay? What we just quickly did right there is what's known as a limiting reactant reaction, or a limiting reactant calculation, okay? With numbers of things that we can see and easily manipulate. As soon as we switch this into atoms, then it becomes a big nightmare and everybody panics. But it's ultimately the same idea. Okay? Questions about conservation of mass? Okay. Let's ignore that. That's even scarier. So let's just go to significant digits. Okay? So this is where we ended Tuesday. All of our digits 1 through 9 are always significant. There is no point at which they do not count as a significant digit. The issue we run into is the case of zeros. Okay, so rule 2 and 3 are both in reference to a 0. And it's what is the meaning of 0. Okay, and believe it or not, this is an incredibly important aspect and something that actually stagnated a lot of science, or our understanding of science throughout history, because we didn't have an understanding of 0, okay, or even negative numbers, even worse. Okay? So what's happening with a 0? It has 2 roles. It has a role of acting as a placeholder, in which case it's just existing there to make sure the other numbers get put in the appropriate columns. Okay? Or it acts as an actual lack of a number. Okay? In the lack of a number situation, it is now a significant digit. If it's acting as a placeholder, all it's there is a placeholder. We don't count it as a significant digit. And I know that's as clear as mud, so we need to come up with some way to look at the numbers to decide when is it acting as a placeholder versus when is it acting as a significant digit. And that's what these 2 rules are. If there is no decimal point, then our 0 has to be controlled by other numbers. Okay? In that case, it's now a lack of a number. Okay? So if we looked at it, our first example, 102. Okay, the 1 and the 2 are absolutely significant digits, okay, because they are numbers 1 through 9. Okay, so they fit that. As for the 0, why is the 0, or how would we treat the 0? Well, we go back to our rules. If there is a decimal point, there isn't one. Or sorry, if there is no decimal point, there isn't one, so we're looking at rule number 2. Then the 0 must be controlled by numbers to either side. Well, we look to the 0 and look to the left. What do we have? A 1, which is significant digit. We look to the right. Significant digit, which means the 0 counts as significant digit, and we have 3. And I did see your hand. Yes.
Do you know you got this?
Yes, I did.
Okay.
We're just reviewing it. Okay, and then rule 3, we went through and decide what's going on if there is a decimal point. So we could jump to, say, the 120 decimal point. Okay. And in that case, what do we decide for our significant digits?
3.
It's 3 because we have the 1 and the 2, absolutely. We look to the 0. We have a decimal point, so we're under rule number 3. If there is a decimal point, the 0 just needs to be preceded by a significant digit. So what's directly in front of the 0? A significant digit, which means 0 is significant, and we've got 3 sig figs. Okay? I then had you go through and do the right-hand column. Since we've already done this, you all know the answers. So let's go through and see what those answers were real quickly. First one. Second one. Interesting. I wonder why we're reviewing it. Third one.
2.
Fourth one.
3.
Okay. It is easy to lose track of sig figs, so we have to go through and make sure we apply the rules consistently every single time. The one where I heard a non-unanimous decision, which isn't a problem, is that second one. Okay. Go back to our rules. 1 and 2 absolutely are significant digits. How about the 0? Okay. We have a decimal point, so we're looking at rule number 3. The 0 needs to be preceded by a significant digit. So we look in front of the 0. What do we see? Nothing, which means not a significant digit. We're stuck at 2. Okay? In theory, the confusion that popped up with that being 2 versus 3 should have popped up again with the other 2. So maybe I scared people into not responding. So let's go through and take a look at those 2, or at least that next one. Minimally, 1 and 2 are significant digits. All right? We now go back to the zeros and try and decide what's going on with those. Rule 2 or rule 3? Rule 3 because there's a decimal point. Start with the leftmost 0 to decide about sig figs. So if we look at that, we have to look what's in front of it. Nothing, which means is that a significant digit? No. We can now move to the next 0. What's in front of it? A 0 that we've already decided was not a significant digit, which means there is no significant digit in front. We're looking at only 2 sig figs.
How about the decimal point?
The decimal point is not a significant digit.
Oh, that's for the, okay.
Okay? So it's there just to decide which rule we're looking at. And the very last one, okay, we might see that the first 2 zeros absolutely aren't sig figs because that's how we ran the first, or the the numbers beforehand. What about the last 0? Why is it significant? Rule number 3, the number in front is a significant digit. It does count. Okay? Getting a semi-unanimous decision through this. So let's try this again. Everybody relatively confident with sig figs now? Yes.
So say on that 0.012,
Yes.
if it was 10.012, now you're all thinking.
Okay, so let's switch that up. So it's a new problem, so I'm going to be changing that last number to now a 10.0120. How many sig figs now? The 1s and the 2s will all be sig figs. Start at our leftmost 0. What precedes it? A 1, which was a significant digit, which means 0 counts. How about the next 0? What precedes it?
0.
A 0 that we said was a significant digit from the previous situation, which means also counts. And the very last one, preceded by a 2, also significant digit. Every single one of the digits in this number are significant, which is 6. Don't laugh at me. It's not nice. I'm kidding. You can laugh. Okay? So a good question. Fairly confident? Think we got a good grasp on it? Okay, let's try and make it trickier. That's always what we do. We've got measurements versus exact values. Okay, and this becomes a little bit more difficult. Okay? When we look at a distance, a mass, or a volume, or a time, they're only as accurate as the device we use to measure them. Okay? So if we use a balance, like in our labs, they go out to the, actually I forget which ones you guys have, either the third or fourth decimal place. Okay? So we will always report our answers to that place, even if it's a big string of zeros, because the instrument is telling us that it is a lack of a number, not a placeholder, because that's what the instrument is designed to do. Okay? But do we have quote-unquote measurements that don't require an instrument? Okay, so the question that I would then ask, let's see, did I actually give the answers on this too? Not quite yet. How many quarters are here? Those are quarters, yes. How many significant digits in that measurement? There are, everybody agrees, 7 quarters, right? How many significant digits are there? What's that symbol? There's an infinite amount of sig figs. Why?
Because anything following the 7, so it'd be .0000000.
There's not 7.000001. Okay? There are exactly 7. If we have an exact number, by definition, it has an infinite amount of sig figs. Okay? So when we go through and count something, we get an exact number. Okay? As long as it's counting something that we can reasonably count. So usually like 7. Or me, less than 5. Okay? I know, that's an extra tricky little thing that pops up in this. And it's going to become more important when we move into conversions. Okay, so let's see how many of you guys remember this. How many meters are there in a kilometer? 1,000. How many sig figs? Okay, so let's write that out so we aren't all thinking about that in our head. There are 1,000 meters in 1 kilometer. How many sig figs in those numbers? It's infinite. Why is it infinite? By definition, those are exact numbers. Those have an infinite amount of sig figs. Everybody happy with that? Okay, so that's a nice little wrinkle to throw into this. So we have to be careful when we go through and look at our measurements. Exact measurements have an infinite number of sig figs. Okay, there is no error associated with them. Okay, so in this case, oh wow, I even picked the 2 exact examples. The amount of quarters and the meters and kilometers. Okay, so when we look at conversions, we have to be careful with where that conversion is coming from. Some conversions give you exact values, some conversions do not. Okay, so be careful when you go through and look at your conversions and deciding the accuracy, okay, for your sig fig calculations. Questions on that, actually? Okay, so now the question becomes is why do we even have to worry about this? Okay, so let's take a look at some mathematical manipulations that we could go through and do with this. Okay, so if we go through and look at this problem, we're going to add up 3 numbers, okay, to get an answer. Once we have that answer, our calculator spits back a bunch of digits to us. Of those digits, only some of them are significant. Some of them are not. Okay? So what does this add up to be? No one give me the number right away. I think it's 115.63362. Psychic, I'm really good at that at math. Okay, so we pumped in the calculator, that's what it spits back at us. If I asked you to provide me the answer to this, and you gave me that answer, are you right or wrong? You're wrong. But the calculator told me that answer. How could you possibly be wrong? Well, it goes back with the accuracy of each of the measurements. We have to apply our sig figs. Please tell me I added that right.
No, I was just gonna say that.
Okay.
Say something else.
Okay. What you're probably going to go to is look at our addition rules. When we add and subtract, the result is only as accurate as the least accurate measurement. So which of these measurements is the least accurate? The very first one is our least accurate. Okay. So our measurement is going to be accurate up to that place. So in this case, I have not 4 sig figs, but I'm accurate up to the tens place in my measurement, which means the number I would report would be those. Okay. Officially, we have to deal with the plus or minus going into it. We don't have to stress about that. Like I said, that's not going to pop up with us again because you aren't having to worry about error propagation, okay, or uncertainty propagation, and that's a whole nother beast.
Would you round up if it was a?
We'll get to rounding as well. Okay. But yeah, in this case, we don't need to worry about rounding because the number that comes after the 6 is relatively small, so we won't round up. Okay? So why do we have to go through and do it this way? All right, well, the issue is that our measurement doesn't include those numbers. So according to our instrument, this could very well be 114.399. How many more numbers do I need? 2 more? 99. Does that change the answer? Quite significantly. Okay, so we could go through and look at what we initially did, and we assumed that there were zeros there. But the instrument doesn't tell us there's zeros there. What it's telling us is that it has no clue what number is there. So with the absolute worst circumstance, all of those things that we assumed were zeros are actually 9s. And if we go through and do the addition up on that, I'll write it a little bit bigger. For those of you that were looking really carefully, you probably see that I gave myself the answers. Versus our 115.63362. Okay. There is a significant difference between those two numbers. Okay. That difference could translate into thousands of dollars, millions of dollars. It could also translate into a measurement being slightly wrong on how long a piece of pipe needs to be or a hose needs to be in a space shuttle. And now when we put it under pressure, the space shuttle loses the hose, and we kind of need the hose there. Okay? So we have to be very careful with how we translate our measurements through. Okay? So be aware of that when you go through and do your addition and subtractions. Are there other mathematical manipulations we could do? Yes? What would those be? Multiplication and division. Okay, you'll notice that this little box only references addition and subtraction. Why might that be? Because we have different rules for multiplication and division. Okay, so not only do you need to know what digits are significant, but you then need to go back to your mathematical manipulations and make sure you translate the significant digits appropriately through those mathematical manipulations. So when we get to multiplication and division, okay, now our answer is only as accurate as the measurement with the fewest significant digits. Okay, that's slightly different. Okay, before we were looking at the least accurate decimal value. Now we're looking at the total number of sig figs. So if we go through and try and figure out the area of this square, how do we come up with the area of the square? Okay, and I do appreciate the people in the back talking. I just couldn't hear you, so thank you in front for responding as well. We're looking at our length times our width. So we just go through and take our numbers. 7.28 units times our, 4.6 units. And our calculator spits out an answer. Immediately, I didn't actually write up what the answer was. Oh, yes, there it is. There's our answer. The calculator spits out that answer. 33.488 units. What's the correct answer? So according to multiplication and division, our result is only as accurate as the measurement with the fewest sig figs. How many sig figs in 7.28? 3 sig figs. How many sig figs in the measurement 4.6? Which is our least accurate measurement? 4.6, which means our answer, according to multiplication and division, needs to have 2 significant digits. So our answer is 33. Officially units squared. Again, we don't have to worry about the rounding because the number that comes after that is a 4, relatively small. Okay? Anybody see how this could be easily confused? Okay. We have to make sure that we understand our sig figs, and then when we go through and do the mathematical manipulations, that we follow the rule to do those manipulations. So when we're looking at multiplication and division, it's dependent on just the number of sig figs. Addition and subtraction looks at the least accurate place. Okay? Questions about that? We run into a similar issue if we go through and drop in a 9 instead of our assumed 0. We get a slightly different answer. Okay, we went from 33 to 34. Okay? Again, that could be the result of or result in a massive change in our overall functionality. Okay? So the next, well, actually before we do that, any questions about any of that? Actually, we can look here. Everyone kind of happy with it? Or as happy as you can be? What if rounding? So now we've got addition and subtraction, multiplication and division again. Okay, if we go through and add up the two numbers that I gave you for the addition and subtraction, in theory you do get 1.335 grams. Okay. How many sig figs should show up in our answer? Okay. It's kind of a mean way to phrase that. Okay. Addition and subtraction goes based on the place, the least accurate place. Where's the least accurate place? The hundredths place. The answer we report is 1.3, and now we've got a questionable number, 3. How many sig figs in our answer? 3. How many sig figs in our least accurate measurement? 2. What happened to our sig figs? They increased. Are we allowed to do that? Absolutely. You'll notice when adding that you have the possibility of increasing the number of sig figs. Okay? But it's still only going to be as accurate as the least accurate place. What about subtraction? Subtraction is going to be almost the same issue, except we can result in the loss of significant digits. Okay? So the next question becomes is what number should actually show up in that underlined position? I wrote 3 there, but why is that questionable? We have a 5 after it. So then it's a question of should we round up to 1.34 or leave it as is 1.33? I don't know. What should we do? Hope somebody came up with a rule. Okay, we'll look at that rule in just a second. How about for our multiplication and division? Okay. Our answer should be reported to how many sig figs? 2. Okay, this one's a little bit cleaner of an answer because in multiplication and division, it's just the number of sig figs. Okay. The fewest we've got is 2 sig figs, so we need to report our answer to 2 sig figs. But we run into an issue. The number that comes after that last sig fig is a 5 again. So we're at the same issue. Do we round up or do we leave it as is? Okay. Deciding what that is, from what my experience is it's dependent on whoever's taught you those rules. Okay. The rules that we're going to work with theoretically in this situation are as such. If our first non-significant digit is less than 5, then our digit remains the same. Okay, so if we got a number less than 5 in that location, it would stay 1.33. If the significant digit was greater than 5, we'll just add 1, so it becomes 1.34. All right? Oops. We have one slight, no, you didn't do that. One slight typo there. What does that rule seem to be forgetting? 5. Rule number 2. Greater than or equal to 5. You round up. All right. So in the case of our addition subtraction, our answer that we would need to enter would be 1.34. Still technically wrong. What's missing?
Grams.
The unit gram. The answer that we would report for our multiplication division would be 37 units squared. Okay. Those two rules, 1 and 2, like I said, those are the ones that tend to change depending on whoever's teaching you. Okay? Trying to match the textbook, and I'm pretty sure the textbook runs it that way as well. Okay? Which brings us to the next issue. Where's your homework based? Is it based in the textbook? Kind of, sort of. I mean, it is the same authors for both, so we would assume that there is an even matchup. They should be following those same rules. Okay? Last thing to worry about. What happens if you have to run a sequence of calculations? Say 15 calculations. When should you round the numbers? If you wait to do it at the very end, you're more likely to keep the correct answer or be as close to the correct answer as possible. If you round it each step of the way, you're potentially compounding the error in each of those measurements. All right, and your answer gets further and starts to drift further and further away from the correct answer. Okay? So when you go through and run a calculation, run it as you would normally with a calculator, punch in all your numbers, get a number at the end, just like we did in these cases. Once you have that number, then go back and evaluate the Sig Figs on everything else. Okay, I know, lots of fun. Questions about that? Okay, I'm going to give you a little bit of practice with this. So here's our practice with this. I was going to make it a quiz. Do you guys want to make it a quiz? Really? Wow. Okay. Then we'll go ahead and leave it off as a quiz. If you've got questions, raise your hand. I'll come around to you. Answer to that first one. Sig Figs? 3. Not 5. There were a lot of people that wrote 5. Why can we not count those last 2 zeros as significant digits? We have to have a decimal point. Without that decimal point, the zeros do not count as Sig Figs, or the trailing zeros do not count.
Okay.
So it's very carefully following those rules. The next number, or number 2. How many Sig Figs there? Yes, 6. I'm going to stop actually counting and sort of cheat. So yes, we end up with...
So what is it?
Whoops. Come back here. 3 Sig Figs, and the next one is 6 significant digits. Okay.
So the 0 that is...
So the zeros in question number 1, there's 2 types of zeros. There is a 0 that is a lack of a number. That's that 0. Okay, with no significant digit, the zeros must be bound by numbers to either side, significant digits to either side. That 0 does have a significant digit, both the 1 and the 2. If we go over to the other zeros, okay, still no significant digits or no decimal point, we have to have a significant digit to both sides.
Oh, it's to both sides, not to do one. Okay.
Yep, and since we only have it to one side, it can't count as a significant digit. Okay, I know it's tricky. More questions on the Sig Fig questions? This first 2.
What if you had like 1, 0, 0, 2, the repeating 0 with no decimal?
1, 0, 0, 2. Okay. That one does get a little bit trickier. You're right in this case, because when we go through and look at that first 0, we look that way. We'd say it's significant, and we look this way, and we're like, uh-oh, what is it? Okay. Both of those do end up being significant. And you almost have to work from both directions in that case, because it's bound over here and it's bound over here eventually, and it's bound over here eventually. Okay, it's a good point. I didn't think of that situation. So in that number, it is 4 sig figs.
Both of them as being one.
Yep.
Okay.
Yeah. It doesn't matter how many zeros as long as there's a significant digit on both the left and right hand side at some point. Okay. Yeah, so I'll have to adjust that rule. I haven't seen that. No one's asked that. It's a good question. So, everybody understand that? How many sig figs in the number 1002? You have 4 sig figs, and we do run into a wrinkle with the setup that I put up for the rules. Okay, but that's, I mean, what's going to end up happening? Came up with a theory and it didn't quite apply to all situations. Okay. What does your calculator spit out for question number 3? Oh, whoops, sorry. I was looking at the wrong answer. 129 point what? 041. What's your correct answer? This is an addition mathematical step, and under the addition rules, we go to the least accurate place, the least accurate decimal place. The least accurate place is the 09, so it's the hundredths place. So when we go through and look at our number, that's our least accurate number.
And there's meters on the end.
There's our answer plus our meters for our unit. Okay, so remember, addition and subtraction go to the place, the least accurate place. Okay, question 4, or questions on that one first. Okay, question 4, what does your calculator spit out? 453 8. It's a whole lot of numbers, which is not going to matter in a second anyway. And meters. Okay. What's the answer you report? 3 sig figs, because our least accurate, or our fewest sig figs, is the one in the middle with 3 sig figs. Which means our answer needs to be reported to 3 sig figs. So if we underline them, 4, 5, and 3 are our sig figs. Okay. We also have to take into consideration rounding. The number that follows the 3 is 8, bigger or smaller than 5? Bigger, which means the 3 needs to become 4. 4, 5, 4. What do we do now? That is all the significant digits we are allowed to include in our answer. We still need the 0, because otherwise it's 454, not 4,000. Okay, that's a significant difference. So we need a 0 to make sure our 4 gets put up into the 1,000 place, not the hundreds place. But now, don't I have 4 sig figs? No, why not? I make sure that I leave out a decimal. There is no decimal place.
So you have to put the 0.
But I have to include the 0. And then our unit was meters. Or sorry, our unit is meters cubed. An m times an m times an m is meters cubed. Okay. If we include the decimal point, what happened? Too many significant digits in our answer, and we're technically wrong. Okay. Particularly in a computer system like your homework. Okay, so watch out for those sig figs. Next one. What do we get as an answer? 0.0252. Let's just throw on some random numbers anyway. Okay, and then our answer is units of liters. What answer do we put in as our official answer? We're doing we're doing an addition subtraction. Our rule goes to the least accurate place, our least accurate place. is the hundredths.
Yes.
The hundredths place, which takes us to our 2. We have to deal with rounding as an issue. We look at the number that precedes it, or sorry, follows it, which is a 5, which means 0.03 liters. Ouch, that calculation really sucked. We started with 4 sig figs in our first number, 5 sig figs in our second number, and after we do the calculation, we end up with only 1 significant digit. We lost a lot of significant digits. Okay. In an actual lab, we would try to avoid that situation by reporting more significant digits off of our measurements so we don't get this loss of sig figs. Okay. The very last one. So this one's tricky because the units are different. Okay. We do not have to do a unit conversion at all. Okay. And in fact, we can't do that unit conversion. Okay. What's nice is we can still run through and crunch our numbers. We can still do that division. We'll address the units here in a second. So if we go through and do 923 divided by that number, 20,312, what do we get?
0.454. 4112.
0.454,112.
4,
Dang it. 4 from the get-go?
4, 5, 4,
4.
112.
3 1s, and 8, 6.
Okay. Again, not going to matter all that much because when we go to now punch this in or put it into our answer, we have to go through and correct for our unit or our sig figs. Sig figs in multiplication and division means 3 sig figs. We go with the smallest number of sig figs. So our answer needs to be reported to 3 significant digits. We've got 4, 5, and 4. Why do we not count those leading zeros? They're not preceded by a significant digit. So our answer is reported as 0.045. This is why I teach organic. I don't have to worry about numbers. 454 as our number. What do we provide as our units? If we can't cancel the units, they stay. Okay? So our answer becomes 0.0454 grams per centimeter cubed. Okay? Questions? Some of you look thoroughly excited. Okay, how important are sig figs? Okay, I keep meaning to ask this question and forget to. So please, everybody, participate in this. How many of you are moving on to 151 or 152? Okay, we got 2 or 4 or 5 of you. Okay, for those of you moving on to 151 and 152, if you take it here, the faculty here are extremely persistent about significant digits. I'm kind of an outlier in that respect. Okay, significant digits are incredibly important, but they are also incredibly inconsistent with how they are applied throughout all of the questions that you may see in your career. Okay? So if you do take it here, and I'm not recommending it, I think you should stay here. Just realize that sig figs are going to be incredibly important to your answers in 151 and 152. Okay? Those of you that don't move on to 151 or 152, you don't need to worry about it. Okay? So now let's push to the next most important question to me. How many of you are moving into organic chemistry, taking 230? Okay, 2 or 3 of you. Guess what? Sig figs show up in organic chemistry. 0. It's awesome. You don't have to worry about sig figs at all. Okay? Those of you moving into 151 and 152 will end up seeing almost all of this again. Those of you jumping directly into organic are kind of left out in the dark, so I'm going to try and spend a little bit more time reviewing the material that's relevant to organic when we get to it. Okay? And I will highlight it as this is incredibly important for organic. Okay? Other questions? Those were my questions. Let's move forward. Let's take a look at some mathematics simplifications. Okay? And this is a suggested thing. You don't have to do this. But if you wrote 4 times 4 times 4 times 4 times 4 times 4 in your notes, okay, that takes a lot of wrist action. You had to write a whole bunch of stuff down. Okay? And if you had to punch that into your calculator, that took a bunch of punching into the calculator. That's a lot of extra work. Okay? Particularly if you punch into the calculator and you make a typo. Now all of a sudden your answer is wrong, and depending on your calculator, you may not even know that you made a mistake. Okay? So we come up with simplifications. We can go 4 to the 6th. Okay? So we can take advantage of the exponents. So now we're saying multiply 4 by itself 6 times. Minimize the amount of mistakes that can show up when you punch it into the calculator, and it saves a lot of wrist work when trying to write numbers out. Okay? So we will take advantage of these exponents. If you need help entering that into your calculator, let me know and I can help you through with that. Okay? So it definitely saves us a lot of time and potentially mistakes. Some other terms that jump up into this, you might hear squared and cubed. What is squared in reference to?
2 power 2.
We're looking at, whoops, keep doing that. We're looking at taking a number and raising it to the 2nd power. That's squared. What's cubed? We're now raising it to the power of 3. Okay? I have no idea where Mike to the x power came from. I'm sure I had a reason for including that. Okay? The next part of this is there are certain powers that we want to take advantage of and use more frequently. The ones that are most commonly used is the power of 10. Okay? So we will raise things to the power of 10 to allow us to get through and show really big numbers and really small numbers. Okay? To do that, it's also going to help us push into scientific notation, which is the next aspect. Okay? So let's take a look at some numbers here. If I wrote out 1,000, that's not too bad. It's only 3 zeros. Stupid counting thing again. Okay? But we could simplify that. I could write that out as 10 to the 3rd. Multiply 10 by itself 3 times, and we get 1,000. Okay, so it saves a little bit of wrist work. With a number like 1,000, it's not that big of a deal. But if we jump up to a number like and why not? Let's add another one. Something like that, that's a lot of extra zeros to go through. So we will use the power of 10 to go through and condense that number down into a simple 10 to the whatever power we need to get through to get that number there. Okay, we'll talk about that when we move to scientific notation. So the power of 10 is something that is very common to show up. We're going to be manipulating and using that fairly frequently. Okay. Where is it going to show up really commonly? Almost all of our metric conversions are based on powers of 10. Okay. Be it 10, deci, 100, centi. So we do tend to use the powers of 10 fairly frequently because in our metric system that we do use for measurements, a lot of them are based off of powers of 10. Okay? So the last part of this would be scientific notation. It's ultimately the lazy way to go through and write out a number that we can then simplify the amount of effort going into it. So if we look at the distance between the Earth and the Moon, what is that, thousands, million, 406,300,000 meters. That's an awfully big number. A lot of different zeros go into that. We don't really like dealing with that, so what we can do is convert that number into scientific notation. So taking advantage of what we understand from our powers of 10, okay, shown here at the bottom, to try and make that number a little bit more manageable to work with. Okay. If we look at the distance between a carbon atom and an oxygen atom and carbon dioxide, okay, that is, I don't even know how to say that one, a really small number. Okay. So what we want to do is pretty much get rid of all of the excess information. That excess information is ultimately just placeholders. So we can simplify our number by removing the placeholders and replacing them with this 10 to the power of. Those placeholders are noted as what number? 0. Okay, so those zeros are our insignificant digits. We can imply all of those by using our power of 10. All right, so how do we go through and do this conversion? Okay. Step 1, we want to place our decimal after the first significant digit. So if we go up and take a look at our distance to the Moon, our number becomes 4 point. All right, now we want to lead out with the rest of our significant digits. Okay, we will include the 0. Why? It's significant because it's bound between two significant digits. Where am I? 4, 0, 6, 3. How about the rest of those zeros? Those are insignificant because we do not have a decimal point and we don't have a significant digit on the far right. Okay? So we've condensed our big long number now into 4.063. Very sloppy looking, but that's what it shows. Okay? We now need to add on our power of 10 times 10 to the 8th power. Okay? We want to go through and look at how far we shifted our decimal point. Okay, we have an implied, where did it go? An implied decimal point here. So we go 1, 2, 3, 4, 5, 6, 7, 8. 8 positions. We now have 4.063 times 10 to the 8th meters. What happens if we look at the distance between a carbon atom and an oxygen? Well, same general idea. We'll go through and say 1.16 times 10 to the, why do you say negative? 5, 6, 7. We're going the opposite direction we went in the first circumstance. Okay, so left to right versus right to left. What does negative mean? This is a weird one. It's the opposite of positive. Okay? I know that sounds, well, duh. Okay. Okay. But it is incredibly important when you go through and evaluate the meanings of different numbers. Okay? In this case, that negative is saying we're going to shift the decimal point the opposite direction we did in the case of it being positive. Okay? And that's pretty much it. So we can take big, long, massive numbers and big, long, small numbers, okay, and convert them into a notation that's a little bit easier to see and potentially work with. Questions about scientific notation? Is that a review? Okay. I would hope so. You look really bored. Okay, so let's switch it up a little bit. This will probably end up being a review as well, but for slightly different reasons. Okay? So what Chapter 2 is looking at is the metric system, and DA is actually standing for dimensional analysis, which is pretty much everybody's least favorite subject when dealing with chemistry, particularly the general chemistry sequence. Okay? That said, if you master dimensional analysis, everything you do this semester as far as calculations is based on dimensional analysis. So if you can figure out the dimensional analysis technique, I don't have to teach you anything. You've already got it solved. What is 151 all based on? Dimensional analysis. 152? Dimensional analysis. So if you can pick up this dimensional analysis method, it will apply to every other chemistry you're going to work with. It is an incredibly powerful tool. However, it is a little bit less intuitive than other techniques, so it does give some people trouble. If you're one of those people, you just need to spend a little bit more time working with it. Okay? So on the basics of our start of Chapter 2, we're looking at measurements. Remember, measurements, all of our measurement systems are arbitrary human inventions. We came in and said, whoop, that was a second. Or, I weigh pounds. Sorry, I got confused. Okay. What system we decided to use as a whole for all science or even all of our communication becomes questionable because we have power struggles and politics that come into play. It's not just, oh, I think this measurement is good. It's, I don't like that person. I'm inventing a new measurement. Now everybody must follow my measurement. And because I'm powerful enough, everybody that believes in me also has to use my measurement, which then puts all of us scientists that couldn't give two craps about either of the people in charge having to convert back and forth between them. Okay? That is now your responsibility. Welcome to science. Okay? So the two common systems we work with are the one that we're apparently calling standard in the US and the metric system that pretty much all science goes through and uses. Okay? The metric system, in my opinion, makes a lot more sense because it is based off of the powers of 10. Whereas our standard system is based off of all sorts of weird fractions and measurements based off of what they had back in the prehistoric era. So in the prehistoric era, what did we have? Oh, I have a foot. Well, I'm going to measure my measurements by my length of my foot. Oh, my thumb happens to be 1/12 the size of my foot, so I'm going to call that my measurement. Okay? We are using measurement systems in the standard system based off of a caveman. Okay? The metric system is slightly more evolved, though feel free to insert whatever opinion you want, but it came back to the French, who went through and decided that we need to quit this nonsense of dealing with the cavemen and come up with a more reasonable system for converting things. And that's where we end up with the units that are listed up here. Okay, and we also talked about this in one of the last lectures. So our standard measurement for length, we're looking at the meter. The standard, or the official standard unit for mass, is actually the kilogram. Okay, the textbook is kind of agreeing with me on this. We want to stick with the gram as our base unit because the kilogram is just a scaling of the gram. Okay, so we can scale everything off of the gram and get to all of our standard mass measurements. Then we have the liter, and then we also have the second, okay, for time. What's nice about the metric system is that we can then scale these off of values of 10 and then assign names to those values of 10 to go through and change our units. Okay? For instance, a tenth of a meter. Centi is for centurion, which is 100. So a tenth is going to be a decimeter. So deci is 10, centi is a hundredth. Okay, so we're looking at 100. Our prefixes end up coming from the Greek, okay, which is odd because the Greeks were the ones that invented the stupid 12th thing. Okay. So we've got a couple interesting things showing up on this figure. Number one, you'll notice that we have a whole bunch of powers of 10 listed out on the right-hand side. Okay? And you've got all sorts of negatives and positives jumping into those. Okay? Because we use some of these more frequently than not, instead of always refer to them as 10 to the third meters, okay, we decided to call 10 to the third a different name. 10 to the third becomes kilo. Because kilo is also too long of a word for us to say. When we write out and do our calculations, we put the K in front of whatever base unit we're using. Okay? So ultimately, all of the conversions that we go through and do with the metric system are all because we're lazy. Okay? And we're trying to convert some really massive number into a smaller number with a different unit. Okay? How many of those units do you need to have memorized? Ooh, yeah, there's a decent amount of them there, and for those of you that remember math, I'm sure there's even more, which I'll get to in a second. Okay, you should really only have to worry about the ones that are most common. The ones that you will absolutely see super frequently would be kilo, centi, and milli. Okay, those are going to happen all over the place. There's no escaping those. So you absolutely need to memorize those. Other ones that typically will show up, you'll see micro show up fairly frequently, but it's not that common. Nano shows up, particularly when we're looking at really fast processes. I did some research where I was looking at a reaction occurring on the nanosecond timescale. Okay, so incredibly fast. Numbers bigger than 1,000, typically don't see them all that often. Why do we not see them all that often? You're working in the lab. How often are you going to work with a teragram? Okay? Or even a terameter. Okay? It's not going to happen because that exposes you to way too much danger for using that amount of chemicals. And it's also ridiculously expensive. Okay? So absolutely nail down your kilo, centi, and milli. You need to have those memorized. Okay? I want to avoid that for the moment. The next thing I want to address as you can pack up, in the math department, when you go through and do math, you've seen these kind of things before, right? Have you ever heard King Henry doesn't like drinking chocolate milk with, who knows, okay? That process of dealing with decimal places, in my opinion, is the worst thing that you could possibly do. Okay? That starts to put you in a pattern of doing a single conversion at a time. In chemistry, you will be doing 4 or 5 conversions. So you can either learn dimensional analysis or you learn a shortcut that gets you 1 step. Dimensional analysis gets you 6. Okay? So be careful with that memorization process. When we start doing conversions, we'll talk about it